Now we move on to the last and fourth section, Fourier Transform, and we'll consider only continuous time Fourier Transform. This section is divided into three subsections. Let's start with the first of them, Introduction to Fourier Transform. Let's understand the idea behind Fourier Transform. On your left is a rectangular pulse periodic signal, and on the right is the frequency response of that signal. Now let's focus only on the middle rectangular pulse and push away all the right and left signals, so much so that the time period tends to infinity. Now we get a graph like this. And now when we sketch the frequency response graph, we get a graph like this. Here we observe that we have continuous values of omega. In that way, we can find a representation for aperiodic signals or signals that are not periodic. So as the period becomes infinity, the frequency components form a continuum and the Fourier series sum becomes an integral. So we are introduced to a new term, Fourier transform, which is given by this expression x of j omega equals integral minus infinity to plus infinity x of t times e power minus j omega t dt. And the inverse Fourier transform equation is given by this equation, which gives back the signal in time domain. Our next subsection is examples of Fourier transform. Our first example is the unit impulse function. Applying the formula from the last slide, we find that the Fourier transform of a delta function equals 1, which means that it is independent of the value of omega or frequency. We are all familiar with the rectangular signal. Note that we don't talk about time period, since in Fourier transform we deal mainly with aperiodic signals, that is signals which are not periodic. And using the Fourier transform formula, we find that the Fourier transform for this signal is 2 sine omega t1 by omega, and the graph is sketched on the right, x of j omega versus omega. In the last slide, we could find the Fourier transform expression to be something similar to sine pi theta by pi theta. Now we define this as sinc theta. Note that sinc theta equals 0 for values like theta equals 1, 2, minus 1, minus 2. Now we move on to the third subsection, which is properties of Fourier transform. Most of the properties of Fourier transform are similar to the properties of Fourier series. So linearity implies ax of t plus by of t will have a Fourier transform equals ax of j omega plus by of j omega. And time shifting implies x of t minus t naught will have a Fourier transform e power minus j omega t naught times x of j omega. The conjugation of the input signal x of t will have a Fourier transform, the conjugate of x of minus j omega. And if x of t, which is the input, is real, then we find that x of minus j omega equals the conjugate of x of j omega. We also find that the even part of the input x of t will have a Fourier transform which equals real part of x of j omega, and the odd part of the input x of t will have a Fourier transform equals j times imaginary part of x of j omega. And the total Fourier transform is given by the Fourier transform of even part of x of t plus the Fourier transform of the odd part of x of t, where x of t is the input signal. This property is different from Fourier series. If x of t has a Fourier transform x of j omega, then x of at, where a is a constant, has a Fourier transform 1 by mod a times x of j omega by a. Substituting a is equal to minus 1, we get x of minus t having a Fourier transform x of minus j omega. Similar to what we had in Fourier series, we have Parseval's relation, which gives a relation between the energy of the signal and the Fourier transform, which is given by this relation. In this equation, the mode of x of j omega squared is often referred to as energy density spectrum of this signal x of t. This property of Fourier transform is quite interesting because the output y of t we get from LTI system is given by the convolution sum x of t convolved with x of t. And this convolution has a Fourier transform y of j omega equals h of j omega times x of j omega, where h of j omega is the Fourier transform of the impulse response and x of j omega is the Fourier transform of the input signal x of t. And with this we conclude. I hope you benefited from this video. Thank you.